James Webb Space Telescope was launched on December 25, 2021, and people all around the world had the telescope in their sight. Since then, we know that the Webb telescope is the most powerful telescope and it is developed to see objects that the Hubble Space Telescope cannot see. But there's a lot we don't know about it, and there's some of the most amazing and novel engineering that's gone into the design and development of this telescope. In this video, we'll present you the 10 facts you should know about the JWST. Make sure you stay tuned to the end of the video to know these facts. They might surprise you. Before we begin, welcome to Discover Space. If you want to be a part of our space journey, don't forget to click the subscribe button and hit the notification bell next to it to be the first to know whenever we upload a new video. Number 10. Lighter than its predecessor. The James Webb Space Telescope is the biggest space telescope ever built, but the James Webb Space Telescope is actually lighter than its predecessor, the Hubble Space Telescope. The Hubble telescope was 2.4 meters in diameter, with a solid primary mirror and a collecting area of 4.0 square meters. But the James Webb is 6.5 meters in diameter, made out of 18 different mirror segments with a collecting area of 25.37 square meters. The Webb has a weight of 14,300 pounds, but the Hubble has a weight of 24,500 pounds, and now it has a weight of 27,000 pounds with its upgraded instruments. This is a tremendous feat of engineering, as practically every component on James Webb, where applicable, is lighter than its predecessor. Number 9. Lightest mirrors of all time. The James Webb Space Telescope has 18 primary mirror segments, and they are the lightest large telescope mirrors of all time. When they were first manufactured, each of the mirrors was in the shape of a curved disc and has a mass of 551 pounds. But by the time they're completed, that mass had been reduced to a mere 44 pounds, which is a 92% weight reduction. The way this has been achieved is amazing. First, a slight mass has been reduced by cutting the mirrors into their hexagonal shape, and practically all the mass on the back side of the mirror is machined away, which is brilliant. All in all, these 18 mirrors will form a single mirror-like plane to an accuracy of 18 to 20 nanometers, making it the best of all time, all with the lightest such mirrors ever manufactured. The Webb telescope is almost half as light as Hubble was. Number 8. Mirrors are not made of gold. The James Webb's mirrors appear to be made of gold, but they are actually made of beryllium. It would have been impossible to manufacture the mirrors entirely out of gold because of thermal expansion. Even at very low temperatures, gold expands and contracts substantially with small temperature changes, making it impossible to use as the primary material for Webb's mirrors. However, beryllium excels on this front. By cooling down beryllium to cryogenic temperatures and polishing it there will be room temperature imperfections, but those imperfections will disappear once those mirrors are cooled again to operating temperatures. However, there's a gold coating applied to each of the mirrors that makes them appear shiny as gold. The gold coating is applied only when the beryllium is manufactured and machined to its final shape. Number 7. Amount of gold used. The total amount of gold in the James Webb Space Telescope's mirrors is only 48 grams. Each one of James Webb's 18 mirrors need to be exceptionally good at reflecting infrared light, and the right amount of gold must be applied. If too little is applied, the mirror won't be entirely covered, but applying too much will start the gold to expand, contract, and deform when the temperatures change. This process of applying gold coating is known as vacuum vapor deposition. In this process, a small amount of gold vapor is injected inside the vacuum chamber, in which the blank mirrors are placed to evacuate the air. The back of the mirror and other areas that don't need to be coated are covered, so that just a polished, smooth surface is coated in gold. This process is repeated until the gold is barely 100 nanometers thick, or around 600 gold atoms. Number 6. Another coating applied. We all know that gold is soft and easily malleable. It's highly susceptible to damage from even a mild or tiny impact. The gold on the Webb's mirrors would be easily affected by small meteoroid impacts and would be unable to maintain the smoothness necessary for the telescope's operation without an additional layer of protection. So, to avoid directly exposing the mirror's gold to space, it's coated in a thin layer of amorphous silicon dioxide glass. That's where the final coating atop the coating comes in. So the function of the glass is very simple in this case: to be transparent to the light and to protect the gold. Number 5. Passive cooling to not above 50 K. The James Webb Space Telescope will observe primarily the infrared light from faint and very distant objects. In order to be able to detect those faint heat signals, the telescope itself must be kept extremely cold. And to protect the telescope from external sources of light and heat, as well as from heat generated by the observatory itself, an enormous 5-layered sun shield has been specifically created. This sun shield will always be between the Sun, Earth, Moon, and the telescope. It's able to be positioned this way because JWST will be orbiting the Sun 1.5 million kilometers away from, but approximately in line with the Earth. Number 4. Cryogenic cooling to cool even more. All of Webb's near-infrared instruments can operate at the low temperatures, in the 36 to 50 K range, that passive cooling achieves. This applies to 3 of its 4 main scientific instruments: the NIRISS, Near-Infrared Imager and Slitless Spectrograph, NIRSPEC, Near-Infrared Spectrograph, and NIRCam, Near-Infrared Camera. All of them are built to operate at 39 K, which is well within the range of passive cooling. But the 4th instrument, MIRI, the Mid-Infrared Imager, needs to be cooled even more than passive cooling can cool it. And by attaching a liquid helium cryocooler to the MIRI instrument, Webb scientists cool it down to the needed operating temperature, which is 7 K. Number 3. Cold temperatures forever. Since it is a closed system, the liquid helium that keeps James Webb actively cool should theoretically never run out. But no matter how thoroughly you protect against leaks, as everyone who has ever worked in experimental physics can attest, they ultimately happen. Webb shouldn't run out of cryogenic cooling if it lives up to its design requirements, as it was built for a 5.5-year mission at the very least, with the option of a decade or longer in the best case scenario. It is always possible that something will go wrong, and we won't be able to actively cool the mid-infrared imager effectively, or for the duration of the mission, which will reduce Webb's sensitivity at progressively longer and longer wavelengths. Number 2. RIP in graveyard orbit. More than 3 decades after its launch, Hubble is still in operation with help from 4 servicing missions. However, that might not be the case for the Webb telescope. Whenever Webb wants to accomplish anything that involves motion, it will exhaust its fuel. The amount of fuel remaining for science operations entirely depends on how well the launch placed Webb on its ideal trajectory towards its final destination. Science procedures will stop when the fuel runs out. However, it can't just be left floating wherever it may go, because that could jeopardize future L2 targeted operations. Instead, just like as the prior spacecraft sent to L2, like NASA's WMAP satellite, it will be dispatched to a graveyard orbit, where it will orbit the Sun for as long as there's a Sun to orbit. Number 1. Potential refueling. It wasn't designed to be serviced or upgraded, but it might be robotically refueled to increase its lifespan. After all of this work, it is unfortunate that Webb's lifespan will be so short. 5 to 10 years is plenty of time to learn a lot about the universe, accomplish a lot of ambitious scientific goals, and prepare for unexpected discoveries that we may not even yet envision. The fact that James Webb will have a lifetime that is cumulatively shorter than the complete amount of its life on Earth, however, seems insufficient given everything it has been through with development and delays. Well, the scientists aren't sitting idle either. If we develop the proper uncrewed technology, we might gain access to a refueling port. The mission's lifespan might be increased by a decade or more with each refuel if we can reach L2, dock with James Webb, access the refueling port, and refuel it. That's all for this video. Thanks for watching. If you enjoyed it, don't forget to like the video. Also subscribe to the channel and hit the bell icon to never miss new content. Also, let us know which fact surprised you the most in the comment section below. Until next time.